Hey guys, in this video I'm going to talk about Lewis structures. Before I go through the rules, how to draw Lewis structures, it is important to know that Lewis structures only show the number of valence electrons, the number and kind of bonds, I mean sigma and p, and the order in which atoms are connected. They are not intended to show the three-dimensional shape of molecules or polyatomic ions. Lewis structures are based on the idea that in most of their compounds, the representative elements, which are group A from the periodic table, achieve noble gas configuration. This is also called the octet rule, because noble gas configuration have 8 electrons in their outermost shell, except for helium, which has 2 electrons. There are some exceptions from octet rules which we will see through this video. Let's start with a simple example that obeys octet rule. Ammonia. First step. We find the number of electrons needed to complete octet. 8 for nitrogen plus 2 for hydrogen multiplied by 3 hydrogens gives us 14 electrons. Step 2. We find the number of valence electrons. For group A of elements is the number of group in the periodic table. So 5 for nitrogen plus 1 for hydrogen, we have 3 hydrogens equal to 8 electrons. Third step. In the third step, we can find the number of shared electrons or bonding pairs. That is first step minus second step. 14 electrons minus 8 electrons equal to 6 electrons divided by 2. We find 3 bonding pairs of electrons. Fourth step. In the fourth step, we can find the number of lone pairs or unshared electrons. That is step 2 minus step 3, which means that step 2 are valence electrons minus shared electrons. So we have 8 electrons from the valence shell minus 6 electrons that are from the shared part, 2 electrons divided by 2, 1 lone pair of electron. Fifth step, we have to build the structure in this step. Central atom is usually the one who has the lowest electronegativity, except for hydrogen that is never a central atom. In our case, nitrogen. When we build the structure, we have to place the other atoms connected to nitrogen in a symmetrical way. We use 3 bonding pairs, 1, 2, 3, and also we use the lone pair, we place that to the nitrogen, because hydrogens are already full. The final step is to find the formal charges. Formal charges are the number of the group of the element minus number of bonds minus number of unshared electrons. As a general rule, formal charges has to be minimized when it's possible for a more stable structure. Let's calculate in our case. For nitrogen, we have group 5 minus 3 bonds minus unshared electrons equal to 0. Formal charges for hydrogen, we have group 1 minus 1 bonding pair equal to 0. No lone pairs in the hydrogen. No unshared electrons. So this is the Lewis structure for the ammonia. Let's move now to an example that breaks the octet rule. Selenium dioxide. First step. We find the number of electrons to complete the octet. 8 electrons for selenium plus 8 electrons for oxygen multiplied by 2, 24 electrons. Second step. We find the number of the valence electrons, which is 6 for selenium plus 6 for oxygen multiplied by 2 because we have 2 oxygens is equal to 18 electrons. Step 3, we find the number of bonding pairs, that is step 1 minus step 2, equal 24 electrons minus 18 electrons, equal to 6 electrons. Divided by 2, we have 3 bonding pairs of electrons. Step 4, we have step 2 minus step 3. We have valence electrons minus shared ones. 18 electrons minus 6 electrons equal to 12 electrons. Divided by 2, we have 6 lone pairs of electrons. Step 5, we have to build the Lewis structure now. The central atom is going to be the one who has the lowest electronegativity, in this case selenium, and we place the oxygens in a symmetrical way. We have 3 bonding pairs, one here, and the other one is going to form a double bond. Let's place now the lone pairs. To complete octet, oxygen here needs 2 lone pairs, and the one in the left needs 3 lone pairs. We have 1 lone pairs remaining. We have to place that to the central atom. We start from the side atoms because they are more electronegative than the central atom. Step 6, we have to find the formal charges. Formal charge for selenium is equal to group 6 for selenium minus 3 bonds, 1, 2, 3, minus 2 unshared electrons equal to plus 1. Formal charge for oxygen on the left, because we have 2 oxygens, one with a single bond, one with a double bond. We have group 6 minus 1 bond minus 6 electrons that are unshared equal to minus 1. And formal charge for oxygen on the right, we have group 6 minus 2 bonds minus 4 electrons, 0. On this side, the formal charge is 0. Selenium, the central atom, plus 1, and the oxygen here minus 1. Again, as a general rule, the formal charge has to be minimized when it's possible for a more stable structure. In our case, we can move 1 pair of electrons to create another bond here. And we are going to have a structure like this. Oxygen, double bond, selenium, double bond, oxygen. Place the unshared electrons. In this case, formal charge for selenium is 0, formal charge for this oxygen is 0, and formal charge for this oxygen is 0. So we see that in this way our compound is more stable. But you have to know, from period 3 in the periodic table and below, we have an expanded valence shell because selenium is in period 4. So for selenium we have a principal quantum number equal to 4. So the subshell number L is equal to 0, 1, 2, 3. 0 stands for S, 1 for P, 2 for D, and 3 for F. So selenium is going to use S orbitals and P orbitals that are required for octet, but also it can use D orbitals to make the molecule more stable. In this case, he has used an orbital from D. That's why he is able to break the octet rule. Here has also the 2 lone pairs. So it is capable for keeping 10 electrons. Let's move to another example that also breaks the octet rule. Sulfate, third example. First step, we have to find the number of electrons to complete octet. 8 for sulfur plus 8 for oxygen multiplied by 4 equal to 40 electrons. Step 2, we find the number to complete octet. So we have sulfur in group 6 plus oxygen in group 6 multiplied by 4 oxygens, but we have also a charge of the ion -2, which means in this case we have to add also 2 electrons. If it's negative, we have to add electrons. If it's positive, we have to remove electrons from the valence shell. So in this step we find the number of valence shell electrons. Step 3 is step 1 minus step 2, and we find the number of bonding pairs. 40 electrons minus 32 electrons equal to 8 electrons divided by 2 equal to 4 bonding pairs of electrons. Step 4, we have to find the lone pairs. Step 2 minus step 3 equal 32 electrons minus 8 electrons from step 3 that are shared electrons equal to 24 electrons divided by 2, we have 12 lone pairs of electrons. Step 5, we have to build the structure. Again, the one who has the lowest electronegativity is going to serve as a central atom. In this case, sulfur, we have to place oxygens in a symmetrical way. The best way is this one. And we have 4 bonding pairs, one here, one here, one here, and one here. We have to place the lone pairs. We have 12, 3 here, 3 here, 3 lone pairs here, and 3 lone pairs here. So we place all 12 lone pairs. The final step is to calculate the formal charge. Formal charge for sulfur is equal, sulfur is group 6 minus 4 bonds minus 0 unshared electron equal to +2. So we have a +2 here. Formal charge for oxygen is equal group 6 minus 1 bond minus 6 electrons equal to -1. So in this case we have a -1 here, -1 here, -1 here, -1 here. And we see that the charge of the ion is -2. 4 -1s plus 2 means a total -2. But this is not the final structure, Lewis structure for this compound, because, you have to minimize the formal charges as much as possible. In this case, the central atom is sulfur, is in period 3, which means it can break the octet rule, because for period 3 we have n equal to 3, L is equal to n minus 1, so is equal to 0, 1, and 2. 0 stands for S, 1 stands for P, and 2 stands for D. S and P, S contains 2 electrons, P 6 electrons in maximum, which means R8, but it has a d orbital, which means that it can place electrons in the d orbital to make the structure more stable. So what we are going to do, we are going to move this pair of electron here to create a double bond, and also this pair of electron here to create a double bond. Let's take a look at the new structure. Sulfur plays a double bond here, double bond here. It remains only 2 lone pairs, 2 lone pairs. One was used to create the double bond. Oxygens here were untouched. Oxygens and lone pairs. Here we have again -1, again -1. Some one of you should ask why we do not place also these oxygens here, these lone pairs here, sorry. We cannot, because the ion has a -2 charge, which means this is the final structure. We cannot do this. It has a -2. But we can do this thing. We can write the resonance structure of this one, that is this one. We replace the double bonds. Sulfur in the middle, oxygen. We leave this one with a single bond, and this one double bond, 1 2 1 2 1 2 1 2 from two lone pairs. So this one are called resonance structures. These two are called resonance structures. Who is the real one is a structure between these two. So as you see, again, in this case, sulfur breaks the octet rule by having 10 electrons on its valence shell. Why? Because it contains empty d orbital, where he can place electrons. Let's move now to a cation that breaks the octet rule. Krypton 3 fluoride plus. First step, we have to find the number of electrons to complete octet. 8 for krypton multiplied by 1 plus 8 for fluorine multiplied by 3 equal to 32 electrons. Step 2, we have to find the number of valence electrons. In this case, we have group 8 for krypton plus fluorine is group 7 multiplied by 3, and we have a cation in this case, an ion that has a plus charge, so it has lose one electron. We are going to remove one electron in the valence shell, remains 28 electrons. Third step, step 1 minus step 2, we find the bonding pairs or shared electrons. 32 electrons minus 28 electrons equal to 4 electrons divided by 2 equal 2 bonding pairs of electrons. We see here that we have 2 bonding pairs. We add another bonding pair to fill the needs for the ion. To have 3 bonds, that is the minimum number of bonds for the ion to exist. It has to contain 3 bonds in order to exist as an ion. We add another bonding pair here. Step 4 is step 2 minus step 3. We have to find the lone pairs. Step 2 is 28 electrons minus step 3. Here we have to consider this bonding pair that we add here, and we have 6 electrons equal to 22 electrons divided by 2. We have 11 lone pairs of electrons. Step 5, we have to build the structure. Again, the one who has the lowest electronegativity is going to be the central atom, in this case krypton. We add 3 fluorine and we place now 3 bonds. Now let's place the lone pairs. Start from the surrounding atoms. Fluorine to complete the octet. Again here 3 lone pairs. We have 2 lone pairs remaining. We have to place them to the central atom. The final step is to calculate the formal charge. Formal charge for krypton is equal group 8 minus 3 bonds minus 4 unshared electrons equal to +1. Formal charges for fluorine equal to group 7 minus 1 bond minus 6 unshared electrons equal to 0. We place 1 here. We see that this is the final Lewis structure for this ion. Because this +1 here, that is the formal charge, is actually the charge of the ion. We cannot minimize it, so we leave it as it is. We have also a case with an incomplete octet. Typical example is beryllium dichloride. Let's build its Lewis structure. First step, we have to find the number of electrons to complete octet. For chlorine is simple, 8 electrons multiplied by 2, plus for beryllium is 4 electrons in this step. Why? Because for beryllium, in order to form bonds, it has to move one electron from s orbital to p orbital by having a total of 2 unpaired electrons, which means he can form 2 bonds with other elements by giving a total of 4 electrons, which is less than 8 that octet rules requires. So we have an incomplete octet. I mean, if you write the electronic configuration for beryllium, beryllium has an atomic number of 4. So we have 1s, 2 electrons here, and 2s, 2 electrons here. But it contains also a 2p orbital that is empty. In order for beryllium to create bonds from its valence shell, it has to move one of these electrons to the 2p. So it contains after 2s 1 electron, and p is going to have 1 electron. So it can create 2 bonds, one from here and one from here, which means a total of 4 electrons. That's why we place here 4 electrons, and it's called incomplete octet. So what do we have? 20 electrons here. Step 2, we find the number of valence shell electrons. We have for beryllium is group 2 plus for chlorine group 7 multiplied by 2 equal to 16 electrons. Step 3, we have step 1 minus step 2 equal 20 electrons minus 16 electrons equal to 4 electrons divided by 2. We have 2 bonding pairs of electrons. Step 4, we have step 2 minus step 3 equal to 16 electrons minus 4 electrons is equal to 12 electrons divided by 2. We have 6 lone pairs of electrons. This is step 4. And step 5, we have to build the structure. Beryllium has the lowest electronegativity, so we place chlorine in a symmetrical way. We have 2 bonding pairs, one here and one here, and we have to place also the lone pairs, 6 for chlorine to complete octet, 3 lone pairs there and 3 lone pairs here. And the final step is to calculate the formal charges. For beryllium is group 2 minus 2 bond is equal to 0, and formal charges for chlorine is equal group 7 minus 1 bond minus 6 electrons equal to 0. We see that the formal charges are 0, so it means that our compound is stable. So this is the final structure for beryllium dichloride. The same happens for boron trifluoride, but in this case the first step has from 4 electrons is going to have 6 electrons. Because that's it for this video, guys. If you find it helpful, give it a thumbs up. See you in the next one. Peace.